Hello and welcome to Milne to LCDM, the continuing series. I'm working on an animation that includes four graphs, x comma t. This is called basically the Milne mapping or the Minkowski mapping, and this is I'm calling this folded out, and what it is it takes these hyperbolas and renders them straight while taking the red lines. There's supposed to be green lines in this too, but they're currently missing. But basically it takes everything and bends it. It takes all of the events on the light cone, which I think are important, an important set of events, and it renders them as a point here, which I think is incorrect, as I try to establish every time I mention this. But then the tau phi comma tau, basically this mapping, it divides this coordinate by tau, so we'll have phi comma tau, and then this mapping, what I did was I took a point here and calculated where is this point here, and then I said, okay, so given that that point here needs to be in a straight line with this, figure out where that straight line would go to, and scale this point by the same factor as I would that point. What that caused was it caused this column to be stretched by this much, bringing this point down to here. It caused this column to be stretched by this much, bringing this point down to there. It caused that column to be stretched by that much, bringing that point down, this point down to there, etc. So what happened in the end was that some of the lines here that were supposed to be not slanted became slanted. So I need to make an adjustment to the code here to do this in a different way, because I'm trying to reproduce certain things made at the www.astro.ucla.edu/tilde-right/cosmo_03.htm, which basically has some of the same, diagrams that I have. The most important one, the Milne version, isn't here, which I consider, which gives me no faith in the rest of the web page, because without that one here to see where everything comes from, it doesn't quite seem like it's right. But here is division has expanded our past light cone. So this is basically what I have in the second to last version, and then this is what I would have in the last version if it were if those lines were straight. So to compare again, comparing these two, I've got straight lines coming up this way. He's got curved lines going up that way. Why? I really couldn't say. Down here in the next part, let me see. Okay, he's got these two graphs. This one shows the light cone kind of like I've got it. I don't know for sure. I don't think if I need to actually put in those subcones eventually to see how that works. But you can see at least the shape of the light cone here is approximately the same as his. But in the final diagram here, the black horizontal lines are going straight across here. I've got the black horizontal lines coming down in diagonals. So what I did before was given phi, find tau of the cone, well, find t of the cone, then find tau of the cone, and then I would stretch it along the tau axis. The thing that I'm going to change is I'm going to say I am given tau, then we're going to find phi of the cone. So looking along there, where is the cone? And then I need to find the ratio, which is represented by tau. Well, it's going to have this length here is phi, and this length here is 1 minus tau. This is going to be phi of the cone, and the tau is going to be same for both of them. We're going to find the ratio, which will be 1 minus tau over phi of the cone is greater than 1. And then that will be how far we stretch our what I'm calling conformal time, and then we'll return from that subroutine. Well, we were given in the subroutine, we'll be given phi comma tau, right? Phi comma tau, and we'll return the same phi and a new tau and a new, will be return phi and the new value of the conformal time. So it's kind of weird because now what I'll have is every point along this line will give me the same value for the stretch of the conformal time. Earlier, when I did it, every point along that line gave a different value for the stretch of the conformal time. So here is the function that I was using previously to do this routine. And I think I can do it, might be able to do this without making too many major changes. See, I'm thinking about the light cone. Up here it's x equals t minus 1, so also this part would be x equals t minus 1, I think. And over here it would be x equals 1 minus t. So this would also be x equals 1 minus t. And then we can erase the top part because we're not really concerned with that. What we're concerned about is with its position from the origin, which is coming up here in the Milne, from the Milne coordinates. And we're imagining, say, this Hubble observer here who crosses this line, and he has a rapidity of phi, and so we're going to call that rapidity phi cone, and it will happen at a certain time, tau cone, even though really these are both properties of this Hubble observer. It's not a property of that light cone. But because that light cone and that Hubble observer uniquely intersect at this time for the Hubble observer that is going at that rapidity, that's going to be what those variables are. Okay, actually, I can work it. Okay, we're imagining a Hubble observer somewhere along that hyperbolic arc who also has the same tau, uh, And we're going to figure out where this point crosses and this point crosses. Well, only one of them really, but there's a symmetry about it. So the rapidity of the observer that intersects this cone here and the rapidity of the observer that intersects that cone there will have the same rapidity, equal and opposite, from the perspective of the central observer. Now there's two ways I could write this coordinate over here. It's t minus 1 comma t, or I could write it as x comma x plus 1. And I can write this one as x comma 1 minus x. So I'm not sure which one I want to use yet, but I do know that phi is going to be hyperbolic tanh of x over t, right? Close. Phi is the arctang of x over t. We also know that tau is going to be the square root of t squared minus x squared. Now, whatever point I choose here, I've got tau. Tau is going to be that where the vertical on this graph. And then I've also got phi, but I also want phi of the cone. Phi of the cone, phi. Okay, I'm not sure if it matters, but I'm going to say phi is arctang of, and I'm just going to use the left-hand side. What do we say? X comma x plus 1. So x over x plus 1, which gets turned into tanh phi equals x over x plus 1, which can be solved as x equals hyperbolic tangent of phi divided by 1 minus hyperbolic tangent of phi. Why is that not helpful? It's not helpful because we don't have phi. Okay, great. That's the key I've been looking for. Did last time. What we need to do instead, we do have tau this time. We don't have phi. So we'll use that same point, which was x comma x plus 1, but this time we'll be doing tau equals square root of t squared is x plus 1 quantity squared minus x squared. And solving that, which comes out to be x is negative 1 plus, or tau squared minus 1 over 2. Then we can plug in phi of the cone is equal to arctang of x over x plus 1, which will be tau squared minus 1 over 2 divided by tau squared plus 1 over 2, I think. Or in just one step, yeah, arctang of tau squared minus 1 over tau squared plus 1. So our new conform is going to have some similarities to the old one, but instead of phi cone staying the same, tau cone is going to be tau. And we're going to be interested in x cone. I don't know if it really makes any difference whether we look for x-cone or t-cone, but for the sake of it being associated with the horizontal variable, I want x-cone to be used, and it's going to be ArcTanh of tau squared, oops, minus 1, squared minus 1 over tau squared plus 1. And not sure how this works, but I thought I'd just stick that little reminder of how I calculated that into there with a semicolon after it so that it doesn't execute. I don't know for sure. But instead of calculating t-cone based on phi arc equals arctanh of x over t, it's going to calculate x-cone based on tau equals square root of t squared minus x squared for cone event x comma x plus 1. Actually, that's not even right. This should have been phi cone right here, because let's put that down here. Phi cone equals that. I didn't delete the right thing. There we go. Delete. So phi cone is arctanh of that. This is actually calculated as tau squared minus 1 over 2. It's not necessary to actually put it in here, though. Tau squared minus 1 divided by 2. And then I think what I can do here is just leave this the same. I'm going to make it an absolute value of this thing. And then down here, I'm going to take out the if statement. Since I got the absolute values in there, it is just going to be, I think it's going to be the negative one, but I'm not 100% sure. We'll just take the negative one because that one should go down from the 1. Well, we've got a map. I think that this is a time for debugging because this is not exactly what I wanted at all. Well, let's give this a shot first. We're just going to change that to a negative because that was a guess after all, and it is looking pretty good, but I do need to fix this central point because it really should be as far down as possible. So I'm going to make an if statement in this, and it's going to go if tau equals 0, whoops, escape tau equals 0, we are going to send tau to like negative 1000. Well, it seems to be trying to be very, very frustrating right now. I might not finish before the end of the video. Huh, this is interesting. I defined stretch upsilon right here, but I never actually used it, did I? So I'm just going to stick that down here, see what changes. But at this point, there's some error that I'm still not getting, and I'm going to leave it at that for now. Thanks for watching.